Morning, everybody. I am Mrs. B Gayathri, working as Associate Professor in the Department of H&S, Tigala Krishna Reddy Engineering College. I am going to teach applied physics. Uh, and in this applied physics, the topic which I am going to concentrate is the laser. Laser, the acronym for laser is light amplification by stimulated emission of radiation. Under this laser topic, we are going to study about Einstein coefficients today. Why we need to study Einstein coefficient is that Einstein was the scientist who has given the theoretical uh, involvement, or we can say theoretical explanation about the stimulated emission. So the stimulated emission is nothing but when the atoms are in the higher energy state, they will not stay there for a longer time. Within that lifetime, if we make the atom to trigger by a photon of energy h nu, then that atom will come back to ground state by liberation of two photons. Such type of emission is called as stimulated emission. This stimulated emission will have highly energetic, highly intensified, highly coherent light, which is called as the laser. So the laser principle is that here we need stimulated emission. In order to achieve the stimulated emission, we need more number of atoms to be present in the higher energy state. That is the population inversion to be achieved. In order to achieve the population inversion, that more number of atoms or the population of the atoms in the higher energy state can be achieved by pumping process, means raising the atoms from the ground state to the higher energy state. That process we call it as pumping. So by means of pumping, we make the population of higher energy state more than the population of lower energy state, because of which population inversion happens. So the population inversion, once it is happening, what happens? The atoms, as we know, the atoms will not stay there in the excited state for a longer time. They automatically they will come back to ground state. So what we want is, we want the atoms to be stable, or it has to stay for a longer time. It has to stay more than 10 power minus 8 second. For that purpose, we need another energy state which is called as intermediate energy state or metastable state. In this metastable state, the atoms which are in the excited state will automatically come back to this metastable state, and they will stay there for a longer time, unless the population will increase. And at that moment, if we induce a photon to hit the atoms in the metastable state, what happens? We are going to have this stimulated emission. This is how the lasing action takes place in laser. So in order to explain about all these things, Einstein has framed, or he has given the expression relating stimulated absorption, spontaneous emission, and stimulated emission. All the three together will give out the expression in terms of constants or in terms of coefficients, called as Einstein coefficients. Let us see the proof for that one. Here we consider N1 be the number of atoms per unit volume with energy E1, and N2 be the number of atoms per unit volume with energy E2. We are considering two energy states, E1 and E2. E1 is having the number of atoms as N1, and E2 is the excited state where the atom number of atoms present is N2. So here small n be the number of atoms per unit volume, and it is at the frequency nu, so that E2 minus E1 is equal to h nu. A photon of energy h nu, E2 minus E1 is considered. Then the energy density of photons rho nu is equal to n into h nu. When these photons interact with atoms, we consider absorption as well as emission. So these transitions will take place, and Einstein clubbed all these three in the form of equation, which is known as Einstein coefficients. So at equilibrium, we consider the upward transitions must be equal to downward transitions. Here, upward transition means the atoms are moving from ground state to higher energy state, which is called nothing but absorption. It is also called as stimulated absorption. Stimulated absorption means the atom which is present in the ground. We know that more number of atoms will be present in the ground state compared to the number of atoms present in the higher energy state or excited state. Now, initially, we make the atoms which are present in the ground state to be triggered by a photon of energy h nu, so that the atoms in the ground state may move to higher energy states. Such type of transition we call it as stimulated absorption. The atoms are absorbing that photon and they will make transition to higher energy state. So the stimulated absorption rate depends upon the number of atoms which are present in the ground state, and it also depends on the incident photon frequency. Okay, if you see this equation, the stimulated absorption rate is directly proportional to N1, and it is also directly proportional to rho nu, density of photons. Okay, now if we remove this proportionality constant by a constant, which is B12, called as Einstein coefficient of stimulated absorption. This is the relation we get for the absorption process. Next one is the downward transition, that is the spontaneous emission. The spontaneous emission means, as we know that by absorbing the photon energy, the atoms are moving from ground state to higher energy state. So in the excited state, the atoms will not stay there for a longer time. They will come back spontaneously to the ground state by liberation of one photon. Such type of transition is called as downward transition or spontaneous emission. So the spontaneous emission rate depends only upon the number of atoms which are present in the excited state. Okay, so the spontaneous emission rate is directly proportional to the number of atoms which are present. N2 are the number of atoms which are present in the excited state, that is proportional to N2. If we remove that proportionality constant, we get a constant, that is A21 into N2. Here A21 is the Einstein coefficient of spontaneous emission. Let us see about the stimulated emission. Stimulated emission means, as we know that the atoms already in the excited state will not stay there for a longer time. Uh, Within that lifetime, if we make the atom to be triggered by a photon of energy h nu, this atom will come back to ground state by liberation of two photons. Such type of emission, we call it as stimulated emission. So the stimulated emission rate mainly depends on the number of atoms which are present in the excited state, as well as the energy density of photons, means the photon energy or the frequency of photon with which we trigger the atom which is present in the excited state. Therefore, if we write in the expression form, we will get stimulated emission rate is directly proportional to N2. It also directly proportional to the energy density of photons. If you remove the proportionality constant, the equation takes the form as B21, a constant multiplied by N2 into rho nu, where B21 is the Einstein coefficient of stimulated emission. If the system is in equilibrium condition, the upward transition must be equal to the downward transitions. Therefore, we club all the three. The upward transition is the stimulated absorption, whose equation is B12 into N1 rho nu is equal to downward transition has got both the spontaneous emission and stimulated emission. Therefore, we add these two. That is B21 N2 rho nu plus A21 N2. We got that expression number one. Now we take rho nu as constant, take it outside. Constant B12 N1 minus B21 N2, A21 N2 as it is. Now rho nu is equal to A21 N2 divided by B12 N1 minus B21 N2, equation number 2. Now, if we divide the whole equation, above equation with the N2 in numerator and denominator, we get the expression rho nu is equal to A21 B12 N1 by N2 minus B21, expression number 3. Now we make use of Boltzmann distribution law, that is already we have seen, we know it as N1 is equal to N naught into e power minus E1 by kT and N2 as N naught into e power minus E2 by kT. Then N1 by N2 can be written as e power E2 minus E1 by kT or e power h nu by kT, equation number 4 under equilibrium condition. So this is according to Einstein, under equilibrium condition B12 is equal to B21. He has considered this, and therefore the expression 3 is also, we apply this term there, and we make use of Planck's law of radiation. That is rho nu is equal to 8 pi h nu cube by c cube into 1 divided by e power h nu by kt minus 1. Wherever rho nu is, this equations when we compare, we will get the final expression as 8 pi h nu cube by c cube is equal to A21 divided by B21. This expression is known as Einstein relation, which gives the relation between the stimulated emission and spontaneous emission, stimulated emission and spontaneous emission. Here, in order to have the stimulated emission to be dominant, the ratio A to 1 by B to 1 should be very, very greater than 1. Then only we will have the stimulated emission. In the case of spontaneous emission, to be dominant, N1 should be greater than N2, and it is this can be possible only in the optical region. This equation is very important uh, in order to explain about the spontaneous emission and stimulated emission and lasing action also. Now, the basic components of laser. So, whatever laser we consider, it may be solid state or it may be gaseous or it may be dye laser, okay, or it may be semiconductor laser. There are mainly the common components which are present in laser are the active medium, the pumping source, and the resonant cavity. These are the three main components which are present in any type of laser. We have to concentrate on the three components. These are called as basic components of laser. Active medium is one where different energy levels can be present to have the population inversion and to have the laser output, and it has to amplify the light. That is called as active medium. Active medium may be solid, maybe gas or liquid or dye, laser dye. It consists of different material. Next is the pumping source. Pumping, as we know, raising of atoms from ground state to higher energy state. It is the energy source that excites the active medium to the excited states, which results in the creation of population inversion in the medium, and hence the laser output will be coming out. This is the pumping source. It is the energy source. The pumping may be optical pumping, electrical pumping, sometimes direct conversion may be possible. So third part, which is essential component, is the resonant cavity. Resonant cavity. Uh, it is fitted at the two sides of the active medium, active medium inside, to provide the necessary feedback for the production of a very intense beam. So active medium is excited by external energy source to produce the population inversion. In the gain medium, that spontaneous and stimulated emission of photons takes place, leading to phenomena of optical gain or amplification. Okay, so in the active medium, the external energy provides the population inversion process, so that the spontaneous and stimulated emission of photons will take place, leading to the phenomena of amplification. So the semiconductors, organic dyes, gases like helium, neon, CO2, etc., solid materials like ag, sapphire, etc., are usually used as lasing materials. Next is the pumping mechanism. So here, this is the active medium, and there are reflectors which are attached to the active medium on both sides. So the excitation source, pump source, provide energy which need for the population inversion and stimulated emission to the system. Examples for pumping sources, as I said, it may be flash lamp or electrical discharge, arc lamps, and light from another laser, chemical reactions, etc., will provide the pumping mechanism. Means the population, in order to achieve the population inversion, the atoms should be raised to higher energy states, which is done by supplying the proper energy to the atoms which are present in the ground state. So this is the pumping mechanism which is taking place here. Next is the a resonant cavity. As we know, in a laser, to generate high intensity outputs, okay, laser itself is producing highly energetic, highly intensified, highly coherent light at the output, which is to be achieved. In order to achieve that one, we need to have a resonant cavity which is fitted between the two ends of the active medium. One is 100% reflecting one, the other one is the partially reflecting surface. It may be the resonant cavity may be having the mirrors, or it may be having lenses, or it may be polished one. So in between these two reflecting surfaces, the radiation is taking back and forth, and hence we will get the highly intensified, highly amplified light at the output, which is nothing but a laser output. So the essential parts, or the essential components of laser are: first one is the active medium, second one is the pumping, the third one is a resonant cavity. Whatever may be the laser it is. Next, we have to concentrate on, let us see about the next type of laser. Different types of laser we are going to see here. The first laser, and the simplest laser which was devised, was the ruby laser, which was constructed by Myman in the year 1960. So it is the pulsed laser. The ruby, the chemical formula is Al2O3 plus Cr2O3, is a crystal of aluminum oxide in which 0.05% of aluminum ions are replaced by chromium ions. So the color of this ruby rod is pink. Ruby laser is pink. The active medium is the ruby rod. In the ruby rod is the chromium, ions. The active medium is the chromium ions. We have to always talk about whatever may be the laser we are considering. First, we have to talk about the active medium. Second is the pumping source. Third one is the resonant cavity. Afterwards, we are going to talk about the construction and working part. The active medium here is the chromium ions, which are actively participating in lasing action. The second part is the pumping source. The energy source is nothing but xenon flash tube, which is wounded on the ruby rod, will provide the will provide the pumping action. Third one is nothing but the resonant cavity, means the end surfaces of the ruby rod. If you see this one, this figure, here this is the ruby rod, ruby rod, and this is the xenon flash tube, which is wounded, which is acting as a pumping source, and there are fully reflected end surface and partially reflected end surfaces, which are acting as a resonant cavity, and hence we are going to have the laser output here. This is the ruby laser construction figure. In ruby laser, the length of ruby rod is around 4 centimeter and 5 diameter is considered. Both the ends of the rods are highly polished and made strictly parallel. They are parallel. The ends are silvered in such a way that one becomes partially reflected, the other end is fully reflected. We have seen already. The ruby rod is surrounded by helical shaped xenon flash tube, which provides the pumping of light to excite the chromium ions to the upper energy levels. As the active medium is chromium ions, so the xenon flash tube will provide the light to excite these chromium atoms to the higher energy states. Xenon flash tube emits thousand joules of energy in few milliseconds. Means it is supplying very huge amount of energy within a span of time. But only a part of that energy is utilized by the chromium ions, while the rest energy heats up the apparatus. In order to cool that apparatus, setting the cooling arrangement is also provided to this ruby rod. So the xenon flash tube is providing, this is the energy level diagram, which for the lasing action to be taken place in the case of ruby laser. Uh, this is this can be explained as a working process by considering this energy level. In ruby rod, ions are the active centers. We all know the chromium atoms are acting as the active mediums here. The chromium ions will be present in the ground state. Ground state. This is the ground state. Now these chromium atoms will get triggered only when a light of wavelength 5600 angstroms from xenon flash tube is made to incident on the ground state chromium ions. Once they get that energy, the ground state chromium ions will be making transition to higher energy state E3 and E4. E3 and E4. The chromium ions undergo non-radiative transitions from E3 and E4. Here, from E4, they will come back to uh, metastable state, and from E3, the chromium atoms spontaneously come back to metastable state, which is called as non-radiative transition. Means radiation is not emitted there, no light is emitted, which is called as non-radiative transition. Here E2 is acting as a metastable state. Okay. Now, which maintain the population inversion. E2 level being a metastable state where population inversion takes place. Any spontaneously emitted photon with wavelength 6943 angstroms would travel in the direction of rod, and if it is moving in the direction parallel to the axis of the rod, then it is reflected back and forth by the silver ends of the ruby rod until it stimulates other excited ions. Now what happens is, now the atoms here, the meta in the metastable state, what happens, the chromium atoms from E1, they will jump to E3, as well as they will jump to E4. They will come fastly to the metastable state, and they accumulate here. Therefore the population of this E2 state, that is the metastable state, will get more and more than compared to the ground state. Therefore, population inversion takes place. And hence, what happens? The stimulated emission is taking place. Therefore, we are going to have the laser output whose wavelength is around 6943 angstroms. So, this wavelength of light will trigger further some more chromium ions to have the pop, to have the stimulated emission. Therefore, we are going to have the multiplication of multiplication of the atoms in the active medium. Therefore, this number of atoms will get increased, and these atoms whose wavelength is around 6943 will get multiple reflections between the two ends of the reflectors. One is the perfect reflector, the other one is the partial reflector, which is attached to the active medium, and hence we are going to have highly energetic, highly coherent, highly amplified light whose wavelength is around 6943 angstroms. So the wavelength which is emitted from ruby rod is around 6943 angstroms. Now the disadvantages of this ruby laser is efficiency of ruby laser is very low. The optical cavity of ruby laser is short as compared to the other lasers. So the improvement has been done in order to achieve, in order to overcome all these disadvantages, and hence the second lasers like helium neon lasers, CO2 laser, and different types of dye lasers have been developed. Now the applications of ruby lasers are in optical photography and for recording of holograms. So here hologram is nothing but three-dimensional picture. So this is done, or the recording can be done by using ruby laser. Ruby lasers can be used for the measurement of plasma properties such as electron density and temperature. Third one is ruby laser is used to remove the melanin of the skin. These are the applications of ruby laser. The ruby laser is the first laser constructed, which is the simplest one. Next is the helium neon laser. Next, we are going to see about the semiconductor laser. Semiconductor, we all know that semiconductor is one whose conductivity lies between conductors and insulators. So semiconductors examples are germanium and silicon are the two examples for general examples for semiconductors. So semiconductors, in order to construct semiconductor laser diodes, we make use of direct band gap semiconductors. So in semiconductors, there are two types of semiconductors. One is direct band gap semiconductor. The other one is indirect band gap semiconductor. In the case of direct band gap semiconductor, the recombination of electrons and holes takes place, uh, and there is a liberation of energy which is in the form of light. Such type semiconductors are called as direct band gap semiconductors, whereas in the case of indirect band gap semiconductors, the recombination of electrons and holes here also takes place, but the recombination will the energy which is liberated is not in the form of light. It will be in the form of heat. Such type of semiconductors are called as indirect band gap semiconductors. So for the construction of semiconductor laser, we consider direct band gap semiconductors. There are two types again, semiconductor lasers. Heterojunction diode lasers and homojunction diode lasers. First one is the heterojunction diode lasers. In this case, we make use of the junction is made up of different materials in two regions, that is N-type and P-type is known as heterojunction. It is made up of different types of materials. A layer of gallium arsenide P-type, that is the third layer, will act as the active region. This layer is sandwiched between two layers having wide band gap via gallium aluminum arsenide P type, the second layer, and gallium aluminum arsenide N type, that is fourth layer. If you see this figure, this is the heterojunction semiconductor laser. Means different types of P type and N type materials can be used for the construction of this semiconductor laser. That is the we consider this heterojunction diode laser. Next one is the homojunction diode laser. A homojunction is nothing but the junction, the P type and N type can be made up of same type of material with different doping. If you see this figure, here P type gallium arsenide, N type gallium arsenide. In between them, PN junction, there is a junction, the depletion region from where laser output is coming. Okay, this is the difference between the heterojunction semiconductor laser and homojunction semiconductor laser. Okay, next is the principle. Here, when a PN junction diode is forward biased, means P type of the material is connected to positive end of the battery and N type is connected to negative end of the battery. It is called as forward bias. Here also we have to talk about the active medium, pumping, and resonant cavity. Okay. Here, in the case of semiconductor diode laser, the active medium is the PN junction. Okay, the PN junction, which is heavily doped. The P type and N type materials are heavily doped so that the junction should be very thin. Okay, we are going to have a thin junction or the thin depletion layer which is formed between P and N type material. Now, this is the active material. Next is the pumping. Pumping means we are supplying the energy. Means we are connecting this PN junction with the help of the battery or the power source is acting as a pumping source here. Next one is the resonant cavity. For the semiconductor diode laser, the resonant cavity is nothing but generally gallium arsenide is used as the active medium. So the gallium arsenide has more reflectivity. Therefore, there are no need of extra mirrors or extra lenses to amplify the output. Therefore, the material itself has it is acting as the resonant cavity whose reflectivity is very large. Like this, we have to explain. We have explained about the active medium, pumping source, and the resonant cavity in the case of semiconductor diode laser. Now come to the principal part. When the PN junction is forward biased, the electrons from N type and the holes from P region cross the junction and they will recombine with each other. Okay, during this recombination process, the light is released in a specific direction, band gap semiconductors like gallium arsenide, I said. This light radiation is known as recombination radiation. Due to recombination, what happens? Light is released, hence it is called as recombination radiation. The photons emitted during recombination stimulates other electrons and holes to recombine. The photons will stimulate the electrons and holes to further to have the further recombination process. As a result, stimulated emission takes place, which produces laser. This is the construction part, P type and N type, which is connected in the forward bias mode. This is the direct band gap semiconductor energy diagram. Okay, EK diagram we consider. Here electron and hole will recombine to give the energy in the form of light. This is the uh, construction P region, and we consider the laser output and PN junction is present here and it is connected in the forward bias mode. This is the construction part, and this is the energy level diagram of P type, and P and N type are sandwiched together. This is the energy barrier. Conduction band is present and valence band is present. There is a band gap. When it is forward bias, what happens? Free electrons are moving towards the junction and holes will be moving towards the junction, and the recombination is taking place here and laser is coming out here. Now this laser light will get multiple reflection between the junction area, between the surfaces, end surfaces of this gallium arsenide, and hence we are getting highly intensified light at the output. Therefore, it is around 8,400 angstrom laser beam can be produced by constraining or by adjusting the energy gap between P type and N type semiconductor. Now, if you see the advantages, it is very small in dimensions, compact and high efficiency, and it is operated with less power than UV and a CO2 laser. It can have a continuous wave output, or sometimes it may be having pulsed output. Main disadvantages are laser beam has large divergence. Because of this large divergence, obviously the purity and monochromaticity will be poor compared to other types of lasers, and it has got a poor coherence and poor stability also. Application says it is widely used in fiber optic communication. So semiconductor laser is mainly used for the fiber optic communication. It is used to heal the wounds by infrared radiations, and also used as a painkiller. It is used as laser printer and a CD writing and reading. These are the applications of this semiconductor diode laser. I think you understood about the today's class. You understood about the Einstein coefficients, how he has correlated the absorption, stimulated emission, spontaneous emission in terms of constants called as Einstein coefficients. Afterwards, we come across the different components of the laser, active medium, pumping and resonant cavity, which are essential parts of the laser, and we have come across one of the type of laser, that is ruby laser, which is solid state laser, and we have seen the working of this Ruby laser applications also we have seen, and semiconductor laser, another type of laser, which is made up of direct band gap semiconductor. Some in some cases heterojunction, in some cases homojunction semiconductor lasers can be used to produce the desired wavelength at the output. So and the applications also we have seen. So I think you understood the topic very well. So thank you very much for uh, for this